My name is Oleg Andreev, and I'm one of the people who are responsible for designing the protocol. And today I'd like to talk about our new programming language for smart contracts. And this talk was gonna contain two parts. First, we need to set the scene for smart contracts, to explain what do we think about smart contracts, because this term sometimes is abused and many people think of different things when they hear those words. And then we'll talk specifically about Ivy as a language and its syntax and semantics. So what are smart contracts? So it turns out that smart contracts as a term was coined by Nick Szabo 20 years ago as a contractual clause that can be embedded in software and hardware and kind of automatically enforced. And he also mentioned that smart contracts actually existed before being identified as such. And the famous example is a humble vending machine that takes in money and gives out the product. And I'd like to look closely at this example because it has some interesting questions that come up. So vending machine is a machine. It's operated by a computer and does implements the algorithm. So the question is, what makes this machine different from all sorts of other machines that surround us? We have computers everywhere. So it turns out that vending machine is a special type of computer or a special type of machine that not only implements the algorithm and moves data around, but it actually depends on the secured property. The vending machine has a logbox that stores product and money and implements the logic for allowing access to this logbox for to buy the product or to unlock the cash at the end of the day to the owner who has the key. So you see that there is this key component that the smart contract is not just the code, but you need some secured property and some way to lock it up so that the computer can have exclusive control over it. So this is our definition of the smart contract. It's an algorithm that works on a secured property. So how do we implement the logbox for digital property, right? We were really interested not in just moving physical things around. There's financial instruments, stocks, money. And to implement the logbox, we need some sort of a protocol to implement secure storage and movement of these digital assets. And interestingly, Nick Szabo also, I think 20 years ago, had another idea which was orthogonal to smart contracts. And he called this idea a property club. The group of owners of a certain digital token can come together on the internet and use a cryptographically secure protocol to keep track of a single shared ledger that respects ownership of every participant. And this was a pretty generic idea, and in the same article later he added that this could be used for another idea of BitGold, but it was not just limited to money. It could track any sorts of property titles. And famously, Bitcoin was the first instance of exact implementation of this property club idea, and it exists for 8 years now. And so what we are doing at Chain, we're doing something complementary to this. So we're driving this idea of implementing the property club for all sorts of other assets with the whole range of security assumptions, settings, and marketplaces. And this is how it looks like compared to Bitcoin. So I'll spend maybe just 1 minute to explain how Chain protocol looks and where the place for smart contract is in this protocol. So the protocol actually is two things. The protocol as just a set of rules. There's a formal definition of what the multi-asset blockchain is, and we have a formal specification for it. There's a federated consensus to implement agreement on the single shared ledger. There is Chain virtual machine, which is implemented. It specifies the bytecode that implements verification of the transfers and issuance of assets. And this whole protocol is an open standard. And the second part is the chain core, which is the software that implements all these things and also adds extra things like key management, management of your privacy of your keys and transfers, and we provide the open source edition that completely implements the protocol. Now, in Bitcoin and in chain, transaction is actually not just an event. Transaction is a concrete data structure. And this is how transactions look like. They are linked, and you can transfer funds from one transaction output to another. So every transaction may have multiple outputs, and each output is referenced by the input. And so the value exists in those outputs. And so you can split and recombine the value. And how do you control authorization? So it turns out that every value is entangled or locked with a particular program. And when you want to make a second transaction, you have to provide some input to this program that satisfies this as a authentication predicate that unlocks these funds and allows them to move further. So how it works exactly? When you come to verify the second transaction, you have to pick up the program that locks the asset currently, pick up the arguments that are provided to this program, put them in the chain virtual machine, and ask it to return a Boolean result. And so if chain virtual machine executes the program with this input and says true, then this particular input is authorized. And you do this for every input in a transaction. And so if all of these are true and transaction is balanced, then transaction is good. And so this is the place where smart contracts kick in. So in this example, it's just a bytecode example of a trivial public key verification. So you have $6 locked with a public key, and then you just verify a signature over the entire transaction with this public key. Interestingly, the virtual machine that we have is pretty rich in functionality because it allows to express not only simple things like, I want this transaction to be signed by one or two or several public keys, but it allows to introspect this transaction. You can check the time, there's maximum and minimum time requirements, and it even can introspect the outputs and check things like, oh, I will allow to unlock this asset only provided there's another input, another payment of a certain amount of maybe some other asset to some other program or some account. And chain virtual machine implements all these bits to introspect transaction. But bytecode is convenient enough to do simple things like check a public key signature. But if you do something more complicated, then it becomes pretty tedious and hard to reason about. And so we are working on the Ivy, which is kind of early preview of the language that is a high-level language that allows to expressing those programs easily. And Ivy is designed specifically to control and define constraints on the secured property. So it's not the generic programming language that allows you to compute arbitrary functions. It's the language of constraints and conditions for controlling the property, expressed digitally. So let's take a look at this simple example of an account. So here we can call an account some program that controls some amount of money, and it's controlled by the public key. So the owner of the corresponding private key can unlock this account and spend it how they want. Very simple example. It's like a key to a vending machine. This is how it looks in Ivy. So first, we start with declaring that this is a program, we call it account, and it's parameterized with a public key, right? So how do we use it? When we want to lock the value with this program, we have to instantiate concrete, instance of this program with concrete parameter, in this case, some sort of public key, and create a transaction that declares that certain value will be sitting together with this program. Then later, we have to choose one of the paths to unlock this value. And the paths also take a parameter. And this parameter has to be specified during spending. So you've noticed that I have this variable. It's a little bit of pseudocode here. So since we're locking $10, we call it an instance of a Hamilton, like a bill. And then we take this instance and say, okay, we want to spend this output, so it's linked here, and we want to trigger this spend path with this concrete signature. And the verifier will feed this in the virtual machine, and virtual machine will run this code and check if this concrete signature satisfies the expression. So this is very trivial, but it shows you the structure that we have a program with parameter and then paths with their own arguments. And so the program is instantiated during locking, and the path is selected during unlocking. Okay, so let's actually implement the vending machine in Ivy. So we call it an offer. So we want to lock some amount of euros that are offered in exchange for dollars. And we want to declare three things. First, the seller, Bob, here, declares his own public key that will be used to control this vending machine. He also declares price and currency. And here I just say USD, but actually it will be cryptographic asset identifier. So this is how it looks in Ivy. We start with a declaration of the program with those three parameters. Who is the seller, what's the price, and what's the what's the numerical price, and what's the asset identifier of the currency. And we declare two possible paths to execute this program when we want to unlock this value. The first path is called lift. It implements buying from this vending machine. So whoever wants to actually buy this, they can provide the payment in their separate inputs, but the only condition that is checked here is that transaction has an output that pays this amount that is parameterized to the account of the seller. And you notice that there is no signature verification. So anyone without communicating with the seller can come in, find this output on the blockchain in this current state, and see that it's sellable and satisfy this requirement and transfer this amount wherever they want. You can also notice that this program does not declare the asset itself being locked. It's like sitting outside of the program next to it in the output. So the program has this implicit knowledge of okay, I'm locking some sort of asset. So it's not important to actually declare it here, pass it from somewhere. And the alternative is that this offer can be canceled by the seller, and the seller can move this asset to the same instance of the contract with a different price, or maybe just move it back to his own account. And there's only one constraint, that the seller, with his own key, must sign that transaction approving this movement. And what happens in the input is that one has to specify which path is being triggered and provide the corresponding arguments. And so all the paths are like a nice syntax for the switch statement, if you will. And now that you get some kind of feel of the language, I'd like to go through a little bit more complicated example to show the power of Ivy and power of chain virtual machine, and show also some privacy aspects of it. And this will be the last example, I promise, but we'll do this step by step. So do you follow so far? Great. Now, this is a bit more complicated. So imagine that one person wants to loan another person some amount of cash in return for collateral that will secure this loan. And we want to construct a program that controls the collateral and provides security both for the creditor and the debtor. So what kind of security we're talking about? Before the deadline, the debtor must have, in this case Alice, must be able to take back her collateral by paying back the loan without communicating to Bob. So if Bob loses his keys or disappears or tries to be not nice, then Alice still can just satisfy the conditions and get back her collateral without relying on any third party. And after deadline, the other way around, Bob, who is a creditor, should be able to unlock the collateral, maybe sell it on the market or move it somewhere else without communicating with the debtor. So those two clauses are security conditions for each of the party in the contract. And so we start with declaring certain parameters that we'll need. We declare the creditor as a public key of Bob, debtor as ls public key, and then we specify the expiration date and payoff amount and its asset identifier. Pretty logical. And the value is not part of the program, it's just being logged with this program. So how this program looks like? It looks like this. So again, we have a program name, enumerate all the parameters, and provide two paths, just like we said. Each path provides security for each party. So the default provides the security for creditor. So it verifies that transaction is time locked in the future after the expiration date. So creditor is not allowed to use this path before this date. And this after clause is based on the transaction introspection. And the second clause is checking the signature that creditor authorizes this transaction. So creditor can do whatever they want. At the same time, before expiration date, debtor can trigger the payoff path, also with a signature, so the debtor authorizes it, but there is another constraint. Debtor is only allowed to do that if they provide the payment of the payoff amount to creditor. So debtor must authorize this transaction, but also must pay, right? So far so good. Now, let's make it a little bit more interesting. You've seen that this is a little bit like kind of stateless program so far, pretty simple. What if we want to transfer the entire contract, like Bob as a creditor wants to just sell this whole loan contract to somebody else, to Carl. But this contract must still respect the security of debtor, correct? We just want to change the creditor value from Bob's public key to Carl's public key, but we shouldn't be able to change other parameters that we agreed to. So how do we do that? We introduce third path that says transfer. And transfer takes two arguments, the signature of the current creditor and this public key of the next creditor. And so what it does is a little bit interesting. It constructs the instance, and remember that the path is triggered during spending, right? So we try to authorize the spending, so the first line is construct the instance of the same program with slightly different parameters. And in this case, we construct this secured loan program with the different creditor, but we respect all the existing parameters. This is important. And then we verify that the entire amount that is currently sitting on the current input, like amount and asset ID, is transferred to this new instance of a contract. So the state of the contract exists in this UTXO set in the unspent output. And of course, we verify the signature of the creditor, so only creditor can transfer it. So you see that this previous line is embedded in the program and respects the security of the debtor, right? And still allows this kind of state transition through parameters through the outputs. And the last thing that I wanted to highlight here is that we obviously see that we can express pretty complicated conditions. And those may involve sensitive information like prices, interest rates, things like that. And we don't want to leak this information generally. So what will be the solution? We could do it in two steps. We can provide another path that will be implementing multi-sig agreement between both parties that have to both co-sign transaction. And then if they agree to whatever they agreed, they can do it without revealing security conditions like prices. And we need to hide all the other paths behind hash commitments or encrypt or somehow. And so how do we do that? So first we declare the path saying agreement, we both agree, we both alive, we both can communicate, and to protect each other's privacy, for instance, if I want to pay off the loan, then I can trigger the agreement statement, sign it, and get the signature of the creditor. So if there is disagreement, then we obviously cannot use this path, but then we have this security paths that violate a little bit of privacy, but provide better security. So if everyone is okay, then we have two signatures, two keys, and we want to verify that the next transaction is signed by both parties. So this is happy case scenario where privacy is not violated. And so how do we do the secrecy of this path? So Ivy has enough structure in the syntax that we can create a Merkle tree out of all the paths automatically. So we can hash independently every path in the tree and only publish the root hash. And whenever someone tries to trigger a path, they would have to provide only the necessary intermediate hashes to prove that this path is actually committed to this tree without revealing sensitive information here. And this facility, you don't need to program it yourself because IV compiler will do this for you. So what this all means is that we're trying to build like a declarative language that automates common security patterns that you want to reuse across all your programs. And it's focused on predicates, the programs that fail or succeed, which makes it pretty easy to make sophisticated tools that analyze safety of the resulting program, because it doesn't compute arbitrary results, it just needs to compute the Boolean expression. And those programs can be used both for issuance and transfer of assets. So you don't only lock funds with such programs, but you also can define issuance rules, and the resulting asset identifier will be linked to the program that you write. And it's possible to compile it not only to chain virtual machine that we're interested in, but also it's fundamentally similar to Bitcoin and Bitcoin script, and we can imagine a compiler that takes this kind of program and compiles to Bitcoin script. And maybe some other applications are possible as well. So to learn more, you can, again, get Chain Core, read about protocol on our website, and contact us at, like on Slack, and Twitter, and support forums. And that's all I got. Thank you.